Okay, what I'm going to do here, I was asked during class period to record a, video of the solving of constants um, for a polynomial for CAM design. And so I'm going to go ahead and proceed with that here uh, so that people will be able to see this and kind of hear me talk it through. So for this particular problem, we have a 6th degree polynomial, and I'm going to go ahead and draw the table for this polynomial. And maybe I should do my best to be neat here. So I'm going to go ahead and try to get some straight lines going and see what we have. Now, for this particular case, we're going to have uh, 7 boundary conditions. And I'm going to go ahead and put those in. Sorry, this can't be even, probably should even be neater than this, but let's see what we have. And so here's our table. And we have our thetas here, our S, our V, and our A for position, velocity, and acceleration. Now, for this particular problem, and again, we're starting with this table kind of already set up here because I'm really focused on solving for the constants, not setting up the table. So I'm going to go ahead and just fill in these values of 0, 80, and 160. These were previously determined, and 0, 0, 0, 2, and 0, 0, 0. Okay, and so this is the boundary condition for a polynomial. Generally, one table per polynomial. Polynomials will always start with 0 in these CAM design problems. Makes it a lot easier. So 7 boundary conditions. That's going to mean that we have a 6th degree polynomial. Now, that's important because it shows us how to go about setting up our general polynomial. And I'm also going to go ahead and set a equation or a variable a, which I'm going to use multiple times. And that a is going to be equal to 80 over beta, which is 80 over 160 or 1/2. Okay, because my beta in this case is equal to 160. Okay, so for this problem, this is a rise, fall, dwell polynomial. And so I have S equal to, and this is a standard S, and we're just going to have it go out to 6 since this is a 6th degree polynomial, plus C1A plus C2A squared plus C3A cubed plus C4 A to the 4th plus C5 A to the 5th plus C6 A to the 6th. Sorry, I got a little messy there. And B. So we take the derivative of that. Now we're taking these derivatives with respect to theta. Oops, I think I've made an error here. I should have said that A was equal to theta over beta. And go back and fix that. So okay, so I wanted to be theta over beta. And I realized that once I was starting to go ahead and take my derivative. So my derivative of V is ds d theta, okay? And so what we have there then is going to be as follows. So our C0 is going to go away. And our C1, remember that A is theta over beta. So when we take the derivative of that A, we'll have 1 over beta. And we'll bring out a 1 over beta from all of these cases. And so we'll have a 1 over beta on the outside here. And then we'll have a C1 plus 2 C2A plus 3C3A squared plus 4C4A cubed plus 5C5A to the 4th plus 6C6A to the 5th. And close parentheses. And our A, so our A is the derivative of V with respect to theta. So wherever we see an A, that is theta over beta. So we take the derivative with respect to beta, we'll have 1 over beta. So that beta comes out again. So since we already had a beta on the outside, now we have beta squared out there. And again, the C1 will disappear because it's a constant, but we have the 2C2 plus 6C3. The 2 comes down, multiplies by the 3, we get 6C3A plus 12C4A squared plus 20C5A cubed plus 30C6A to the 4th, close parenthesis. Now, when we go to solve for the constants, what we're doing here is we are looking at our table and plugging in it. Every place we see a number in our table, that will represent an equation. So we're going to have really 7 equations here to help us solve for these different values. So let's go ahead and get started with that. So the first one we have is an S equal to 0 right here. So we just start at the top and go across, right? And so what we're going to do is we're going to plug in the theta equals 0, because that's when theta is equal to 0, S is equal to 0, right? And so everywhere we see a theta, and again, every one of those A's has a theta in the numerator, we're going to place a 0 there. And so I'm going to start with the S. And so at theta equals 0, my S is going to be equal to, and I plug in zeros wherever there's an A, because again, there's a theta in the numerator of all those. So basically the only thing I have there is a C0. Now at theta equals 0, S is equal to C0, but S is also equal to 0 at that point. And we got that from our table again, right here, right? So what we found is that our C0 is indeed equal to 0, okay? Now, what's the next one? The next item that we need to look at is our V, right? Now at theta equals 0, V is also equal to 0, right? And we just see that in the table. But when we plug in, when we look at this equation here, right? And we plug in a 0 for all the A's, we'll have V equals 0 equal to 1 over beta times C1, because everywhere there's an A will disappear. So that means that our C1 has been found to be equal to 0 also. Okay, and so we found so far that our C1 and our C0 is equal to 0. Now let's go further and look at our A. Okay, so at theta equals 0, our A is also equal to 0. And so A is equal to 0. And when we look at our equation for A right here, we see that we'll have 1 over beta squared and 2C2, but every other thing there disappears because they all have A's. And so that means that our C2 is also equal to 0, because the only way that equation can be equal to 0 is if the C2 is 0. So far we've found 3 of our constants. We found the C0, the C1, and the C2, but they're all equal to 0. Okay, great. Okay, so what do we do next? The next we do is we turn our attention to the S equals 2. That's at theta equals 80. And so let's go ahead and set that up. So again, looking at an S equation, and actually I would love to have some of these equations on the next slide. So let me copy these to where, actually, we should probably copy this entire slide. We need all this stuff on my next page, pretty much. So I'm gonna try to copy this. Doesn't always work well when I'm trying to do these copies. So let me just hope that I get a decent copy here. Okay. Okay, so lots of my stuff came over, and let me make it a little bit smaller so I can have a little bit more room here. Okay, so we'll see how that looks. Okay. Okay, so moving right along. Okay, erase this down here. Leave that there. Okay, so the next thing we want to look at here is our 2, right? And I'm going to go ahead and grab a different color just to not be too messy, but just kind of emphasize what I'm doing here. So at theta equals 80. And remember, 80 is beta over 2. But when theta is equal to 80, S is going to be equal to 2. Now let's look at this S equation. Okay, so we already know that the C0, C1, and C2 are gone. They were all found to be 0 previously. So when I plug it in, remember there's every A is theta over beta. Now, in this particular case, theta is equal to 80. So that means that our A's are equal to 1/2 beta over beta, right? 1/2 beta over beta. Interesting, right? So what we have then is a 1/2 for A. Okay, so every one of the A's is equal to 1/2. And so when you look at the equation that's left here for S, we'll have 1/2 squared. I'm sorry, we're starting with the C3. So we'll have 1/2 cubed, because that's A cubed, times C3, plus 1/2 to the 4th times C4, plus 1/2 to the 5th times C5, plus 1/2 to the 6th, that's my C6. And so I have 4 unknowns still, C3, C4, C5, and C6. And I've handled the S equals 2 position. Next thing I want to look at is at theta equal 160. And I'm looking at this position here. Then at that point, I know that S is equal to 0. Now, when theta is equal to 160, that means that theta is equal to beta. And so now my A, get rid of this one, my A is now equal to theta over beta, but theta is equal to 160, which is beta. So now I have beta over beta for A. And that means that my A is equal to 1. Okay. So if A is equal to 1 and my S is equal to 0, again, I need to look at my S equation, which is my top equation here. Okay, just kind of emphasizing that. Actually, let me take that out. Just kind of wanted to focus your attention here. But if S is equal to 0, then I should have 0 equal to C3. Again, the A is 1, so I'm just going to not write the A there. I'd just be writing 1 cubed, plus C4, plus C5, plus C6. Now I turn my attention to V. At theta equal to 160, V is also equal to 0, right? And so 0, now look at that V equation. Here's my V equation. Just focused in on the second equation right there. And I will have a 3C3 plus a 4C4 plus a 5C5. Oh, and I almost forgot my 6C6. Okay, not including the A's again, because every A is 1. Last but not least, my acceleration. My acceleration is equal to 0 when theta is equal to 160. So I turn my attention here to my acceleration equation. And I'll have 6C3 plus 12C4 plus 20C5 plus 30C6. So if you look at that, I have 4 equations, right? And so I'm going to go ahead and do another color here and label these equations. So this equation here with my S is my equation 1. This is equation 2, equation 3, and equation 4. Now, these equations can be solved with a matrix. We've done that a few times, but let's go ahead and set that up here. And so I'm going to go ahead and copy these equations that I just wrote and get them onto my next page. Okay. So those are those equations that I just wrote there. And let's go ahead and put them in a matrix form. And so what we have here then is a matrix where we have a C3. Whoops, let me make it bigger. I need more room here. C3, C4, C5, C6. Now that's the vector. Here's the matrix. So the first row is going to be my S row. And so the C3 here is multiplied by 1/2 squared, and then a 1/2 cubed, and a 1/2 to the 4th, and a 1/2 to the 5th, and so on. So a 1/2 cubed is 1/8, and a 1/2 to the 4th is a 1/16, and a 1/2 to the 5th is a 1/32nd, And last but not least, a 1/64 form a 1/2 to the 6th. So that handles my S equation. So my equation 1 is done. Now look at equation 2. Each one of those is multiplied by 1. So I just have a 1 in each location for my equation 2. And that's equation 2 right there. I just handled my S equals 0 equation. Now for my B equals 0, I have a 3, then a 4, then a 5, and then a 6 multiplied by the constants. And last but not least, my A equation. That's going to be a 6 and a 12 and a 20 and a 30. Okay. Now, when we do these, when we multiply this matrix times this vector, we get everything that the S, well, we get basically this information, right? And so for my S equation, when I multiply the 1/8 times C cubed and add it to the 1/16 times C4 and so on, I'll have S equals to 2. When I do the same for equation 2, I'll have S equals 0. When I do the same for the third equation, I'll have 0 for B. And for the fourth equation, I have 0 for A. And so those are all the items that I have. And so that's how I would, to solve for my constants, I would take the inverse of this matrix. And so I have MB, let's say MBB. Then what I'd say then is that B was equal to M inverse times B. And then I'd have solved for all of my constants. And we usually do that in MATLAB. Now I want to show one other thing in terms of solving for constants. And in this case, I want to solve for the constants in a critical path motion problem. It's slightly different. And so I'm going to do that now. Oops. Okay. So now, well, I'm going to turn my attention to critical path motion, but this problem was a standard a symmetrical rise, fall, dwell problem. So now let's take a look at a critical path motion problem and see how it differs in terms of finding your coefficients. So I'm going to label the CPM, and that stands for critical path motion. And this is actually a part of example, oops, this is from example in your textbook 8-11. And one of the segments in that example had the following table. And get that table here. So theta, SVA. And in that particular example, we had the following boundary conditions. Nothing here, nothing there, 10, and a 0. Okay, so we have 4 boundary conditions, so this is going to be a third order. Now, it proceeds similarly, but let me also start by saying that the velocity that we have is 10. That's in inches per second. Okay, that's an important thing for us to realize. Also, our theta dot, our cam angular velocity in this problem was it was basically 1 rotation every second. So 2 pi radians per second. Okay, so 2 pi radians per second. And as you can see, our beta is 30 degrees. Ooh, that doesn't look so much like 30. Let me clean that up a little bit. You're probably saying, he's never neat. Why is he doing that? Okay, so 30 degrees. Okay, so let's go ahead and set up our S, B, and A equations such that they are up to the third power. So C0. Now, one thing that's unique about the critical path motion is I'm generally going to use an X. So that's one difference. You remember before I was using an A. So X squared plus C3 X cubed. Now, when we take the derivative of this, we are no longer taking the derivative with respect to theta. We're taking the derivative with respect to time. And again, that's because we're doing critical path motion. And so ds dt, and that's going to require that we know what the derivative of x is. And what is x? I didn't even say what x was. So x is equal to theta over beta. okay? And again, our beta is equal to 30 degrees, or pi divided by 6, okay? And if I take the derivative of that x with respect to time, I should have theta dot over beta. I've already said that the theta dot is 2 pi over 1 second. And my beta is pi over 6. So those pi's going to cancel. So that means I end up with 12 radians per second for my x dot. And that's important. So when I take my derivative of b, I should have a c1 x dot plus a 2c2 x dot plus a 3c3 x squared. X dot x squared. Oops. Oh my goodness. This is kind of messing up. 1 second. Let me write it the same way I wrote the other one. So I'm going to have my x dot second. Okay. And so there's my derivative. Now I need to do a acceleration. So that's the derivative of the velocity with respect to time. Okay. Now this is going to require, we have some x double dots. Now, what is the x double dot? If x dot is 12, then x double dot is 0. Okay. Now there is no theta double dot, and that's the reason, right? And so if you look at this, x dot was theta dot over beta, then x double dot would be theta double dot over beta. But there is no theta double dot. We're assuming a constant rotation of our cam. And so we have 0 for x double dot. And so for A, we'll have a 2c2 x dot squared plus a 6c3 x dot squared. Okay, and so we have a S, B, and A equation here. Okay, so we have 3 equations. So we're going to go and do the same thing we did before in terms of determining these constants, of which we have 1, 2, 3, 4, C0, C1, C2, and C3. We have 4 constants, and we have 4 equations. And so let's look at the first equation. So this is our first equation we're going to set up. So we're going to say then that our S, and let me go ahead and use this color. So at, oops, let me start where I did it last time. So at theta equals 0 degrees, S is equal to 0. And now I turn my attention to this equation. I'm going to put a theta equals 0 in for all of my x's. Now remember, for the x, theta is in the numerator. And so wherever there's an x, it's going to go away. So I'm going to have a C0 plus C1 times 0 plus C2 times 0. So there's nothing else to include there. So what we found from our S equation is just that C0 is equal to 0. Then we do our B. So at theta equals 0, B is also equal to 0. And so we look at our B equation, which is this equation. And wherever there is a x, it's going to go away. So we're going to have a C1 x dot, but there's x's in the next 2 pieces, so we're not going to have anything there. So we just have a C1. Oops, but what is the C1 equal to? We don't, well, if the equation has equal 0, and we know x dot is equal to 12, then that means that our C1 is equal to 0. So far we found 2 of our constants, the C0 and the C1. Now we turn our attention to the A equation. And now at that one, we're actually looking at a different, actually I'm kind of moving ahead too fast. We need to turn our attention next. There is no A to look at in the 0 for theta equals 0 position. So what we look at next is we drop down to the second row of our table and we look at the theta equals 30. So at theta equals 30, we have a B equal to 10 inches per second. Now, what about this equation for B? Okay, and so when we look at that equation for V, putting in a 30 wherever we see an X, now that's a beta, right? So if for when, oops, let me say it like this, for theta equal beta, then we should have X equal to 1, right? Because we'll have beta over beta, and X dot, remember, is 12. And so we've already found that C1 is 0. So we'll have 2 C2, 1 for X, X dot, that's a 12. Plus, so we just did this one. Now we're going to turn our attention to this guy. Okay, and so that's going to be plus 3 C3 X squared, or 1 squared times X dot, which is 12. And so there's our equation for the B. 2C2, 12 plus 3C3 times 12. Okay. And last but not least, we should turn our attention to this A at theta equals 30. Now I'm kind of running out of space, but I'm going to go ahead and squeeze it in. So at theta equal 30, which is beta, A should be equal to 0. Okay. And now let's look at that equation. So we have 2C2 X dot squared. Now 2C2 X dot is 12, but it's squared in this equation, plus 6C3 times X, which is 1, times X dot squared, or 12 squared. Okay, so we have 4 unknowns. 2 of them we found, and that was found here and here. But we have 2 equations left, this equation and this equation. So we have 2 equations, 2 unknowns, so we should be able to solve, right? And so let me go ahead and copy what we have for those 2 equations and make sure this is not gonna be super neat, but let me just bring that to our next page so we can have it there for us to look at. Okay, and so I'm gonna rewrite those equations just so they'll look a little neater. And so let's see what we have here. We have a V equal to, actually that's 10, I'm sorry. Well, I'm gonna go ahead and write that. V equals 10 inches per second equal to 24 C2 plus 36 C3. And A is equal to 0 inches per second squared. That's going to be equal to, what do we have there? 2 times C2, that's 24. Oh, I'm sorry, that's a 12 squared. So that's 144 times 2, or that's going to be 288. Plus, that's a 12 squared times 6. That's an 864 C3. Okay, so those are my 2 equations, 2 unknowns. And so I'm going to put those in a matrix in the same manner I did previously. So C2, C3. Whoops, ooh, that's messy. Okay, and here's the matrix. So for the B, I have a 24 and a 36. And for the other one, I have a 288 and an 864. And what are those equal to? They're equal to a 10 and a 0. Now, we could have just gone ahead and solved this equation, right? Define our C2 and C3. We could just solve these 2 guys, right? 2 equations and 2 unknowns isn't that hard for us to do. So if we just go ahead and solve those, we'll find that our C2 is equal to 5/6. And our C3 is equal to negative 10 over 36. Or that might be better written as negative 5 over 18. Okay, so what is our S equation? Remember, C0 and C1 were already found to be zeros. So our S equation ends up being equal to, what's on the previous page, but I still have it here on the top of mine. So it's going to be C2 or 5/6 times X, or theta over beta, and that's a squared term, minus 518 times the theta over beta times a cubed term. And of course, we also could write down our velocity and our acceleration equations in similar fashion now that we know all of our constants. Okay, so that's the conclusion. We have done both the solving for the polynomial coefficients for a standard, like a single rise, fall, dwell, and for a critical path motion CAM problem, which is a little different because we're differentiating with respect to time. In the simpler case, we are differentiating with respect to theta. So these are two different ways of going about it. So hope you enjoyed that. See you next time.